Welcome to the deep dive. I want you to think about the charging cable for your phone or your laptop for a second. It's thick, it bends awkwardly, and, eventually those internal wires just fray and break.
Oh yeah, we've all been there with the duct tape on the charging cord.
Exactly. And inside that plastic casing is copper, which is heavy, rigid, and frankly, easily oxidized. But what if I told you the heavy, rigid copper wiring that powers, well, basically almost every aspect of our modern world is actually an obsolete technology?
I mean, it's a pretty wild thought. We have spent the last century and a half pulling millions of tons of heavy metals out of the earth just to build our power grids and our devices. Copper has kind of been the undisputed king of electricity.
Right, but looking through the stack of research you shared with us this week, it really seems like that reign might be coming to an end. Today, we are looking at a thread. Literally a thread lighter than a feather, flexible as cotton, but capable of carrying vastly more electrical current than solid copper.
Which is, quite frankly, the holy grail of material science.
Sure.
For decades, researchers have been trying to figure out how to replace heavy, bulky metallic wires with microscopic supermaterials.
Which leads to a really strange question. Why do we still rely on heavy metals for electricity when we apparently have microscopic supermaterials right in front of us? Well, today we are unpacking a brand new, incredibly detailed research paper published in the journal Nature Communications to find out.
Yeah, and it's a fascinating study.
It really is. Our mission for this deep dive is to uncover how a team of scientists finally solved what I can only really describe as a microscopic traffic jam, creating the ultimate wire for the future of flexible electronics.
To understand the sheer magnitude of the breakthrough in this paper, you kind of have to look at what scientists have been struggling with for over 30 years. The foundation of this new material relies on something called carbon nanotubes.
Okay, carbon nanotubes.
Right. In theory, they are the perfect conductor. But in practice, they have been an incredibly frustrating scientific mystery.
Let me stop you right there, just so we're all on the same page. I know we've got some material science fans listening and know exactly what that is, but for the rest of us, what are we actually looking at when we say carbon nanotube?
So, think of a sheet of chicken wire. But instead of galvanized metal, imagine that hexagonal grid is made entirely of carbon atoms, bonded together in a perfect flat plane.
Okay, I think I can picture that.
That is called graphene. Now imagine rolling that flat sheet of atomic chicken wire into a microscopic, seamless cylinder. That cylinder is a carbon nanotube.
So it's basically a hollow pipe made entirely of carbon.
Precisely. And at the scale of a single individual tube, the physical properties are almost miraculous. I mean, they are astonishingly strong, virtually weightless compared to metal, and they conduct electricity with zero resistance.
Zero resistance, wow.
Yeah, the electrons can just zip straight down that perfect atomic tube without hitting any bumps at all.
Because there's no turbulence, right? It's like a perfectly smooth highway.
Exactly. It's called ballistic conduction. But the problem arises the exact moment you want to make a usable wire out of them. A single microscopic tube, which is, thousands of times thinner than a human hair, doesn't really do you much good if you want to wire up a laptop.
Right, you can't plug a single atom-thick tube into the wall.
No, you can't. To make a wire you can actually hold in your hand, you have to bundle billions and billions of these tubes together into a macroscopic string, which is called a carbon nanotube fiber.
Ah, I see where this is going. When you bundle billions of tiny pipes together, you create that microscopic traffic jam I mentioned earlier. I was reading through the background in your notes, and I really like to think of this as a train system.
A train system is a great analogy.
Yeah, so imagine those individual carbon nanotubes as high-speed bullet trains. The electrons are the passengers. On a single train, they are just flying along at top speed without a care in the world.
Yep.
But to get from one end of a long wire to the other, those electron passengers can't just stay on one train. The tubes aren't infinitely long, so the electrons have to constantly jump from one tube to another where they physically touch.
And those junctions, the physical gaps between the individual tubes, they ruin everything. Suddenly, your high-speed bullet train hits a massive, totally disorganized transfer station.
And it all slows down.
Exactly. When the electrons try to jump the gap, they scatter, they experience resistance, they lose massive amounts of energy as heat, and the overall electrical conductivity of the fiber just plummets. It ends up being dramatically lower than a basic, solid copper wire.
So if you're an engineer looking at this traffic jam, what's the first instinct? Like, how did people initially try to fix this?
Well, the initial attempts were incredibly brute force. Scientists thought it was purely a structural problem. So they tried a process called solution-assisted wet stretching.
Wet stretching.
Yeah, which is essentially soaking the fibers and pulling them taut to force all the microscopic tubes to align perfectly parallel. They also tried mechanical densification.
Okay, mechanical densification. That sounds like a very polite academic way of saying they just squished the fiber as hard as they could.
Honestly, that is basically what they did. They ran the fibers through rollers to pack the tubes tighter together, trying to minimize the physical gaps. They even tried creating a core shell hybrid by coating the carbon bundles in actual metal.
So you're just cramming the trains closer together so the jump between them isn't as far. But based on the charts in the paper, that didn't solve it, did it? The conductivity was still nowhere near copper.
No, it wasn't. The structural fix just wasn't enough. The contact resistance at those junctions is incredibly stubborn. So when squishing didn't work, the field moved on to chemical fixes. They started experimenting with a process called doping.
Okay, let's unpack this. Let me make sure I understand doping in this context. They introduced foreign chemicals into the fiber to add more charge carriers, basically putting more passengers onto the bullet trains to try and force more electrical current through the system.
Yes, exactly. They treated the outside of the carbon fibers with highly reactive chemicals, things like strong acids or halogens like iodine and bromine. And initially, the lab results were thrilling. The electrical conductivity spiked massively.
But there was a fatal flaw. I mean, you read the real-world performance data in the sources, and it just falls off a cliff.
It really does.
Think about painting a car with water-soluble paint. It might look amazing sitting safely inside your garage, but the first time it rains or it gets too hot or you take it on a bumpy road, that chemical upgrade just flakes off or washes away. You're left with a mess. Are you telling me they essentially painted a microscopic race car with watercolors?
That is a brilliant way to visualize it, yes. The chemical dopants were only sitting on the outside surface of the carbon nanotubes. They were exposed to the environment and weakly attached.
Oh, so they just wear off.
Exactly. Over time, in ambient air, or when exposed to moisture, harsh solvents, or even just regular bending and heating, those crucial dopant molecules would degrade, evaporate, or detach entirely. The fibers would lose their superconductivity in a matter of days.
Which means they were totally useless for the real world. You can't put a wire in an airplane if it loses its conductivity the first time the temperature changes.
Which brings us to the core scientific mystery our researchers faced. How do you permanently upgrade a carbon nanotube? Like, how do you get the chemicals to actually stay put in a chaotic, real-world environment?
So how did scientists figure this out? Because the solution they came up with requires a completely new way of thinking about the architecture of the fiber itself. This is where the story gets really interesting.
It does.
The team behind this breakthrough, Dr. Tongzhao Sun, Dr. Mukong Jian, and Dr. Jin Zhang, along with their colleagues from Peking University and Ningxia University and the Beijing Graphene Institute, they published this brilliant two-step process in Nature Communications. They call it a synergistic doping strategy. And step one is all about creating doors.
Right, because they realized that if putting chemicals on the outside of the tube was like water-soluble paint, they needed to get the chemicals onto the inside.
Sounds impossible.
It's extremely difficult.
Yeah.
The problem is that carbon nanotubes are naturally closed, incredibly stable structures. The carbon lattice is a fortress. You can't just pour a chemical inside.
But the paper says they used plasma to get inside. They took these pristine carbon nanotube fibers and blasted them with an inductively coupled nitrogen plasma.
Wait, hold on. If you blast a microscopic atom-thick tube with a plasma laser, wouldn't you just obliterate it? How do you poke a hole in something that small without destroying its structural integrity?
It is a very delicate balance, which is why the nitrogen plasma is so crucial. They're not taking a blowtorch to it. Inductively coupled plasma allows for extraordinary precision at the atomic level.
Oh, okay.
They tune the energy so it only knocks out a few specific carbon atoms along the side of the tube, creating they call sidewall defects.
So they're basically just knocking out individual bricks in the fortress wall. Yes, but they aren't leaving gaping holes. The plasma treatment actually integrates nitrogen atoms into the carbon lattice right at those defect sites. This is the first part of the synergy. The nitrogen acts as an active chemical anchor. It reinforces the doorway.
Wow. That sets the stage perfectly for step two, which I like to call the Trojan horse. Now that they have microscopic nitrogen-reinforced doors, they need a payload to sneak inside.
And for the payload, they used a chemical compound called molybdenum pentachloride, or OCl5. They put the nitrogen-doped carbon fibers and the many Cl5 into a vacuum-sealed glass tube and heated it up to 300 degrees Celsius.
That's pretty hot.
It is. And in a vacuum, this causes the MCl5 to sublimate. It skips the liquid phase entirely, turns directly into a vapor, and diffuses toward the fibers.
And the vapor enters through those sidewall defects. The MCl5 molecules bypass the outside of the fiber and go entirely inside the hollow cavity of the nanotube. The paper uses the term endohedral encapsulation.
Yes, endohedral encapsulation.
Whoa! Endohedral encapsulation. That's a mouthful. You basically mean they built a ship in a bottle, right? The bottle is the nanotube, and the ship is the chemical they snuck inside.
What's fascinating here is that ship in a bottle is a perfect translation. The chemical payload is safely encapsulated within the carbon walls. And remember those nitrogen atoms forming the door frame?
Yeah, the anchors.
Right. To play a crucial role here, the nitrogen actively promotes the absorption of the MCl5. It essentially acts as a chemical magnet, pulling the vapor inside and locking it in place.
I'm looking at the charts and the sources you sent us, and the term charge transfer effect keeps coming up regarding this MCl5. I need you to translate that for me. Why does putting this specific chemical inside the tube actually increase the electrical conductivity? Like, what is happening at the atomic level?
Think of the MCl5 as a powerful molecular magnet for electrons. When it is locked inside the carbon tube, it strongly interacts with the carbon lattice surrounding it. The MCl5 pulls lazy or bound electrons out of the carbon structure and forces them into the conduction band, what we can think of as the fast lane of the highway.
Ah, so it's not just adding more random passengers to the train station, it's actively pulling electrons from the surrounding structure and accelerating them, drastically increasing the density of charge carriers flowing through the tube.
Exactly. Because the MCl5 is physically constrained inside the tiny diameter of the nanotube, its molecules form tightly packed, one-dimensional chains. This highly ordered structure maximizes that electron pulling effect. It is a stunning piece of atomic engineering.
It really is. They built the microscopic doors, they snuck the chemical Trojan horse inside, and they locked it down to pull electrons into the fast lane. The big question is, did it actually work? Give me the numbers.
The results were staggering. They measure this using a metric called specific electrical conductivity, which is conductivity relative to the density or weight of the material. The fibers achieved a specific electrical conductivity of 14,166 Siemens square meters per kilogram.
And since carbon is vastly lighter than dense metal, its specific conductivity just destroys the competition. It surpasses the specific conductivity of solid copper by 115%.
This is incredible.
It also beat gold, zinc, and silver. And when they tested the current carrying capacity, which is, how much raw electrical power you can push through it before the wire melts or fails, it beats solid copper by 28%.
But here's the best part. They didn't just beat copper in performance. They solved the durability mystery that had plagued this entire field for decades.
Right, because the ship is inside the bottle. The MCl5 isn't sitting on the outside like water-soluble paint anymore. It is physically trapped inside the indestructible carbon armor of the nanotube. The bottle takes the damage, while the chemical upgrade stays perfectly safe inside.
Yes. And to definitively prove this, the research team put these new synergistic fibers through a literal gauntlet of environmental torture tests. Why? Because the real world is brutal on electronics.
Oh, absolutely.
They left the fibers sitting out in ambient air for 50 days to see if the chemical would evaporate. It didn't. They ran them through cyclic thermal stress, rapidly heating them up to 200 degrees Celsius and cooling them down repeatedly, simulating the extreme temperature swings inside an engine or a high-performance computer.
And they physically bent the fibers 2,000 times to simulate the wear and tear of a charging cable or a wearable device. They even dunked them in harsh chemical solvents just to see if they could wash the dopant out. And through all of that abuse, the electrical conductivity barely dropped. The performance was permanently locked in.
The external environment simply couldn't reach the delicate dopant molecules hidden inside the carbon cavity. The structural integrity of the tube protected the chemical upgrade from oxidation, moisture, and friction.
So let's pull back and look at what this means for you listening to this right now. It means we have a thread, a literal thread that you can spool up and weave on a loom. It is vastly lighter than metal, it's stronger than steel, it conducts electricity better than copper, and it is practically indestructible.
And materials dictate what is technologically possible. Every major leap in human civilization, the Bronze Age, the Iron Age, the Silicon Age, is defined by the materials we master. Replacing copper fundamentally changes how we build technology.
In the paper, the researchers highlighted a few immediate applications. The first one is wearable tech and fibrous heaters. They took this new carbon nanotube material and wove it into a multi-filament thread that used that flexible thread, which looked exactly like regular sewing thread, to wire up a circuit and successfully light up 4 light bulbs.
Which is amazing. But the heating application is perhaps even more impressive because of its incredible conductivity and thermal stability. When they applied just 3 volts of power to this fiber, it heated up to nearly 400 degrees Celsius in a matter of seconds. And it cooled down just as fast when the power was cut.
Wait, 3 volts? That's like 2 standard AA batteries.
It is a minuscule amount of power, but because the internal resistance of the fiber is totally optimized, that low voltage converts to immense controlled heat.
So you could have an invisible weightless heating system woven directly into the fabric of a winter jacket or a deep-sea diving suit. No bulky metallic wires to snap when you bend your elbow. No heavy battery packs required. The fabric itself is the heater.
Exactly, and that leads to a very interesting secondary phenomenon. When a material is this highly conductive and interacts with electricity this efficiently, how does it react to the ambient energy floating around us in the air, like radio waves, Wi-Fi, or cellular signals?
Oh, that's a good point. If this material is an electron superhighway, what happens when external electromagnetic waves crash into it?
It creates powerful electromagnetic interference shielding, or EMI shielding. Highly conductive materials act like a mirror for electromagnetic waves. When a wave hits a highly conductive surface, a physical phenomenon called impedance mismatch occurs.
Impedance mismatch.
That's right. The wave can't penetrate the material. Instead, it bounces off. Because these new carbon nanotube fibers are so extraordinarily conductive, they are incredible at reflecting EMI.
And the researchers actually wove these fibers into a plain textile. It just looked like a piece of gray cloth. But when they tested a double layer of this fabric, it provided an incredible 92.7 decibels of electromagnetic interference shielding. I know decibels can be a bit abstract, but the researchers provided an amazing real-world anecdote in the paper to prove how powerful this is.
Yes, this part is brilliant. They took a standard smartphone and placed it on a wireless charging pad. As expected, the phone began to charge. Then, they took a thin piece of this woven carbon fabric and slipped it between the charger and the phone.
And it instantly and completely disabled the wireless charging.
Completely blocked it.
The power efficiency of reflection for this textile was nearly 97%. It just bounced the magnetic field from the charger right back.
To put that in context, that level of shielding is considered exceptional, far exceeding the requirements for commercial and even many military applications. It's almost entirely blocking the X-band frequency range.
Think about the future impact of that across industries. We're talking about revolutionary changes in aerospace. A commercial Boeing 747 has over 130 miles of copper wiring inside of it. That wiring weighs thousands of pounds.
And in aerospace and satellite design, every single ounce of weight costs thousands of dollars in rocket fuel to launch into orbit. If you can replace hundreds of pounds of heavy copper wire with a flexible thread that weighs almost nothing but conducts electricity even better, you save massive amounts of fuel.
You increase payload capacity.
Exactly. It fundamentally alters vehicle design.
And it's the exact same principle for electric vehicles. Range anxiety is the biggest hurdle for EV adoption. A heavy wiring harness drags down battery efficiency. Lighter wiring means a lighter car, which means that same battery can take you much further on a single charge.
We have spent centuries reliant on a heavy metal to carry our electricity. Now we are looking at a future where our power flows through carbon, the very building block of life itself.
So, to summarize the incredible journey we've been on today in this deep dive, we started with a microscopic traffic jam. Electrons were struggling to jump between carbon nanotubes, creating a transfer station bottleneck that made the overall fiber worse than basic copper. Past attempts to fix it by pasting chemicals on the outside failed because they were too fragile, like water-soluble paint in the rain.
But by looking at the fundamental architecture of the material, this team found the answer. They used inductively coupled nitrogen plasma to open atomic doors, and then used vapor transport to build a ship in a bottle, hiding the MoCl5 molecules safely inside the nanotubes.
They turned the carbon's own structure into an impenetrable shield.
Exactly, creating a hyperconductive, indestructible fiber.
Over 14,000 Siemens square meters per kilogram of specific conductivity. A 115% improvement over solid copper.
If we connect this to the bigger picture, it really raises an important insight about the nature of problem solving itself. True innovation often isn't about adding more brute force to a flawed system. You don't just keep painting the car with better paint or squishing the wires harder.
No, sometimes you have to look at the fundamental architecture and change it from the inside out. By simply moving the chemical from the outside of the tube to the inside, everything changed.
It really did.
It is a beautiful reminder that sometimes the biggest breakthroughs happen at a scale we can't even see. Which leaves me with one final thought for you to mull over. If we now have a material that conducts electricity better than copper, is stronger than steel, and is light enough to weave like a piece of clothing, well, what does this mean for the frontiers we haven't been able to conquer yet?
Oh, that's a big question.
Right. Engineers have dreamed of building a space elevator for decades, but no material was strong enough and light enough to stretch from the Earth to orbit while carrying power. Or what about the future of cyborg biology? If we need to wire computer interfaces directly into the human brain, we can't use rigid, oxidizing copper. We need a biocompatible, indestructible microscopic thread. And it turns out scientists may have just invented it. Thank you for joining us on the deep dive. Be sure to follow and subscribe for more incredible science stories unfolding in real time. Catch you on the next one.